the difference. I entirely agree with you. You're completely correct. There's so much to learn from viewing a numerical experiment. Most of the research in solar physics, I mean, for instance, let me give you one example. There's a paper published maybe 10, 15 years ago showing that they found a spicule inside a simulation in which the spicules can't actually be made because there's too much diffusion in the calculation. A spicule is a very, very thin thing as measured by it, and yet they claimed to see a spicule because they found something that looked like an ellipsoid structure coming out from an active region, and said this was actually equivalent to a sort of 20-to-1 aspect ratio spicule. I think that kind of thing is delusional. I mean, and in particular, if you're using a very diffusive calculation to find things that aren't, by definition, that survive without diffusion, I think you've got a problem. I'm well known for this kind of skepticism, so you know this is a very typical talk of mine, except that I hope I made it more coherent.
I think we agree on that one. Difference between.
I mean, I have enormous admiration for what Matthias has done with Muran. And I think actually Matthias would be one of the first ones to say that it is a numerical experiment, right? I mean,
yeah, I mean,
it's not something you really want to go and compare with observations unless you're pretty damn sure about the things you don't know about.
I mean, there are a lot of things you don't capture these relations experiments.
That's the interesting stuff.
Yeah.
That's where it gets really interesting.
But the interesting thing is that you nonetheless get a lot of features the sun has, even by not capturing a lot of the microfilm.
Yep.
So there is some robustness in there, and I think that's something which is worth by studying. Why some of the things we can observe are so robust and kind of agnostic of a lot of the smaller scale things you cannot capture. Are we just getting lucky, or does it have a deeper meaning?
What a great question. There are lots of young people in here that would really benefit from working with you on that, I think.
Thank you, Phil, for the talk. I'm gonna go towards something. You claim that the secret is hidden somewhere in the spectroscopy, polarization, magnetic fields, if you want a tangible subject. Why do you think our community has not been keen on exploring observations of coronal magnetic field across these 8 years?
Well, yeah. First comment, the measurement of the coronal magnetic field by itself is not, given the restrict, if we could go in with a magnetometer and wave it around, fantastic, like we can in the Ionosphere, because we have these spacecraft. I mean, that would be, and the solar wind, right? That's perfect. The thing is, most of the energy that's dumped into the corona is going into radiation from the base, and that's not accessible to a magnetometer, so we got remote sensing. Given that the coronal heating problem is related to thermalization of ordered motion and ordered energy in magnetic. I mean, after all, magnetic energy is just the ordered motion of electrons versus protons, but it's filling the region in space around it, according to, you know, Theo Savart and all these other people. So you've got ordered motion being converted into that, and that's and that ordered motion can be on ridiculously small scales, because the MHD system that we've got is driven by things like granulation, by God help us, chromospheric reconnection, you know, ion neutrals. These things don't always smooth out the structures that are coming up. Sometimes they can generate more of them, and that's one of the ideas, is you can drive the solar wind with kilohertz frequency waves generated by fast reconnection in small structures at the top of the chromosphere that then drive the waves away. It sounds like I'm getting away from your point, but what I'm trying to say is that the coronal heating problem is one aspect that I think is not primarily the reason to go and measure the magnetic field in the corona. Because you're never going to see, if you can barely measure the magnetic field, you're not going to measure that little B perk part, right? So what can you measure? Well, the ingenuity of people to see oscillations is very powerful because that gives you the B if you know what the N density is. But then if you think about the models people have proposed, you've got all these strands everywhere. Now, these are all at different phase speeds and everything. So what the hell, and densities. So you can't have them both at the same time. You can't have a coherent structure that's, moving and saying that the magnetic field strength is 10 Gauss and it's got a density of 10 to the 8. If at the same time you're describing that with a bunch of incoherent small scale structures that are little ribbons or current sheets of what do they call threads, right? A multi-thread model. I mean, so to get back to your point, the coronal heating problem is not good. What it is really good for, and where I think, Maurice showed me an example earlier today of polarimetry changing as a CME is erupting, and it's changing with time. And so the dynamics of the corona, I think, is really, really interesting to study with the magnetic field measurements. In terms of why people haven't done it, it's bloody hard. The radio has been doing it for decades, but they're stuck because their measurements are pretty much restricted to things over 200 Gauss. So you're looking right down the throat of an active region, and you've got no idea where the surface is because it's a resonant phenomenon. So you're kind of, but it's very interesting. In doing the kind of work, we've been doing together and that other people are working with, and that Maurice is working with. I keep mentioning Maurice. He just came to my office immediately before the talk, which is what
Yeah, especially your brain.
Yeah. So I think for coronal dynamics, it's really, really desperately important to do that. And so I think the reason that it's been difficult is because the coronal lines are very broad, right? Top. The magnetic fields are weak. That means that the ratio of the Zeeman splitting to the width of the line is very, very, very small. And it's hard enough to do it in the damn chromosphere where the temperatures are 100 times smaller. So, and the field strengths are larger. But I showed you some measurements there. Those are very high signal. Those are signal to noise 50 to 1 or something of the line of sight magnetic field in the chromosphere. So I think that's the reason why. But I think you're right on the cutting edge here. I think with DKIST, once they figure out, I mean, we heard a talk from Sarah Yeagley yesterday on the which instrument is it? The DL NERSP, and then we have the cryo NERSP, and I think of a NERSP as some kind of elf-like structure that in a cartoon or something. So those I think eventually should, if they can get the signals scattered light down enough, really, really. And so for you guys, you should be really excited about the opportunity given with that stuff. Comp, again, has the complementary ability of doing synoptic. Cosmo potentially could do the same thing. Personally, I don't know what the status of Cosmo is. I mean, whether it'll happen or not. But those things, if you really want to know about the origin of space weather events at the Earth, this is what you've got to do. Now, one of the really nasty things about it is that you, even using the Zeeman effect, you never know whether the magnetic field coming at you in this component is going that way or that way. But that's the prime thing you want to know for geo-affective events. So what you need to do is fly a spacecraft away from the Earth sunline and solve that problem by observing the Zeeman effect from two different viewpoints. Because it's degenerate observing just from DKIST.
I have, yeah. Oh, yeah. Okay. I have a quick question. Since you started your career studying stars, stars have grown as well.
Yeah.
And the astrophysics community kind of buries it under the rug, and they're like, "Oh, we observe these UV lines, blah blah blah," and then we make these very detached inferences about the habitability. And I mean, if you look through the literature, how they try to reconstruct coronal models, they don't even do like semi-empirical models. They just have some correlations between UV indices. So, what do you think are the prospects to inform better our astrophysical colleagues about what's happening on other stars? Because we know certain stars, like blue or hotter stars, they have thermal winds, but they don't have coronae, right? You need a surface dynamo to have a corona. So,
well, I think the advantage they have is that they have 10 to the 11 of these things in a galaxy, right? I mean, we have one. But what we have is the ability to understand processes that they don't. And it's not just because the angular resolution is better, it's because, we have much higher signal to noise ratios. But some of these people are dastardly clever. I mean, there's something called LSD, which is not what that's the Rolling Stones thing probably, but LSD is least squares decomposition. It's a technique of using thousands of lines from the photosphere of a star to build up signal to noise. And so you just sit there for a few hours or an hour or a few minutes or something. And suddenly you get these time series measurements of evolving magnetic field, and they can see changes in the polar fields as the star cycle goes from this direction to that, which is less cancellation than in the toroidal components, which always have a signal opposite polarity on the disk. So, I mean, I think they have what they need to understand stellar. I don't think life on Earth depends. I mean, I know I said it at the beginning. Would we have life without a corona? Yeah, I think we would, right? I mean, it's under the ocean. But will we have multicellular life with big brains and all that stuff? Well, my mind is not just pointed at somebody else. But yeah, no, that's a really interesting question. And I think there's actually a great deal of benefit to work with both communities. I was lucky to do that very early on. But then I realized that some of the data I was analyzing with the techniques I was using was so non-unique that it was like, I'm asking the wrong questions. But that's not always the case. For instance, we really know about stellar evolution because of the Hertzsprung-Russell diagram. And I mean, we get rid of all the systematic uncertainties by doing an observation of a cluster and assuming it's this shape and it's that far, everything's that far away. So we know exactly what state of evolution is. I mean, stellar evolution theory is so sophisticated. I mean, it's like equally miraculous to me as the standard model of particle physics is that we understand how well nuclear fusion works inside stars and how they evolve. So you can do a lot of stuff there, and it's so exciting. I mean, and it's not necessarily a lot of investment of time, because what you'll find is coming from the solar community is that all these details you're looking at, these guys don't care about it. They don't know anything about it at all. And so you can actually go in and say, hey, no, look, this is actually really interesting. You missed it. So I encourage all of you to think a little bit broader. Basically, my message today is that I was given the opportunity to become a broader scientist as I could. I learned one hell of a lot from people like B.C. Lowe, Andy Scumanich, Grant Athay. I mean, these are all people at HAO. And it was so rewarding for me. I don't think I would survive today, but I wouldn't get appointed to a position today anyway. Within HAO, it's different. So protect your specialized work, but don't do it at the expense of enjoying the research you can do in a broader context.
Two quick things. One, from the habitability question, the stellar magnetic fields, one of the things that they're considering is just using fine-axis probes. So you mentioned, magnetometers being waved close to the sun. There are close-in not super close, it can't be that close to the star, but in a manner of speaking, they are these very close-in exoplanets potentially can be used as probes in a manner of speaking. That's one idea that I like, although they aren't getting down to the fundamental physics of that problem. It's just an idea that they're throwing out there. But an actual question though, you mentioned a lot about the Alfvén waves, and I haven't read enough Alfvén waves papers to fully understand your concern. If you're saying that the phase speeds are about 2,000 kilometers per second, and the line widths are about 20 kilometers per second, are you getting it? I guess I don't understand the concept. If the plasma is frozen in with the Alfvén waves, and you're referring to the phase speed, but not the oscillating speed.
Yeah.
So wouldn't it be the oscillating speed that matters when it comes to the line widths, or are you referring to like phase speed because of the reflections happening as the refractive indices change.
I see.
That's okay.
I see exactly where you're coming from, yeah. I think what I was saying more, that the Alfvén speed is characteristic of reconnection.
Mhm.
And I apologize if I conflated too many things together in one with that.
Well, I just haven't read
So,
enough on the.
Yeah, no, you're right. The side-to-side amplitude has nothing to do with any Alfvén speed. It has to carry a certain amount of energy up. And for Alfvén waves, the group speed is the same as the base speed. So you end up with, for a given flux of energy, and you have to have an oscillation in velocity, and during that oscillation, the wave period tells you how far it's moving. So that tells you how much bending of the field lines there is, and that number can be more or less anything. So there are certain numbers that would fit into that picture, and people say, oh, it's compatible with Alfvén waves because 10 kilometers a second carries plenty of energy because it's moving at the Alfvén speed. So it's carrying a small oscillation at a very fast speed, much faster than the sound speed. It can heat the corona. That's a wave heating model. What I was trying, and I confused you with, was the fact that the Alfvén speed is the speed at which a system will relax if after reconnection of topological change. And so if reconnection is important, then it's saying that only a small fraction of the magnetic field is being reconnected. So that, for instance, if you have a magnetic field that's mostly in one direction, and if this, so Parker picture has two field lines. This is the sweet Parker configuration, but this angle can be anything. So what a nanoflare is just this angle snapping back to that. And then, so you can see that the reconnection jets come out here, but you've got the initial magnetic field and you've got a tiny perturbation. It's only the energy associated with this tiny perturbation that's converted into this. So, for instance, a vertically propagating Alfvén wave, reconnection at the limb, you should see Alfvén jets moving backwards and forwards. Fiber. I
didn't think about the geometry.
No, it's a really good question. I mean, I'm sorry if I completed things.
Thanks.
Any other question? Anyone? From online?
But the online people have all gone to sleep.
There are 46 audience, which are noted as world record.
World record.
What was?
World record.
46 online.
The chat.
Oh.
A world record of 46 people.
Oh. Well, I did a bit of advertising.
You can say something about the movie that you have up there.
Yeah, yeah, as you can see, this is a what the hell? Oh, I need to go to the window. Why should you believe anything I say when I can't even run a Mac? I mean, So this is from a movie of about the minute goes past every 9, 51, 2, 3, 4, 5. So this is an hour and a half's worth of data. And while this is perhaps not the best screen to show it on, I mean, I can see some sprinkling of things here, which are much better seen here, where this is just noise, right? That's fairly weak emission. This is an edge enhanced, an enhanced thing done by the group in Belgium. And what I really just wanted to point out was, people say that the corona is so dynamic, and certainly you can see things going on here. You can find things that are doing this. But if we look at typical loop structures, your eye is drawn to see things that move. I mean, as a hunter or gatherer, I'm colorblind, and people like me survive because we can still see motions. If I was a gatherer, I would have died because I wouldn't have been able to tell a blackberry from a nasty fungus or something. You know what I'm saying? So we're very, very much trained to see things that change. And yet the quantitative analysis I did of some data similar to this showed me that almost nothing is going on, and by in these structures like this, and so let's see, can we see? Would anybody like to point something out and say, oh look, that's dynamic?
There's a few small things, but
Yeah. So, yeah, the coronal is certainly dynamic, but oh my God, let's not get carried away. I mean, you have to look at the data first and foremost. And it is an observationally driven subject, this. There's too many degrees of freedom for the plasma for us to do much else. So this really struck me as being, you know, I went to ISI in Switzerland, and Nuruddin Rawafi was presenting some stuff from here saying, oh, it's all dynamic all the time and you can't do anything. He showed me a picture of the photosphere obtained with a movie of about 3 hours, and it was coming and going all over, but it only lasted about 10 seconds. And most of the photospheric field you see doesn't actually make it into the corona. I mean, a lot of it is granular fields that turns over before it gets anywhere near the corona. So I'm just struck by this, and I would love to be proven wrong and shown that my analysis is a result of line of sight averaging along here and not something else. But, you know, I don't know how to do that without stereoscopy and stuff like this to see what's going on. But yeah, the corona is not very active. And yet there are these active regions everywhere. And it's all a question of time scale, right? Alfvén crossing time is a few seconds. Yeah. 20 megameters would be 10 seconds. 100 megameters would be 50 seconds, okay? And yet this is an hour and a half worth of data. So anything going on in Alfvén time would immediately kind of go in 2 or 3 time steps, or no. Yes. So and yet they look steady. Again, you've got line of sight problems all the time. Corona is almost always altitude thin, so you just see straight through everything and just add everything up. And maybe my assumptions aren't correct, but at least I say what the assumptions are and try to make some progress. So I don't believe in nanoflares at this point.
Well, do you believe in pico flares?
Well, only to the extent that you postulate that emission must be due to individual quanta of energy release. It can be explained without that. For instance, by something like the very large number of resonant surfaces that dissipate across the magnetic field. So if you imagine making a cut across any of these MHD structures, so I take a slice through there, the things we see have high densities. One of the puzzles is why they're organized like this if they're dissipating on very small scales, because you're saying, well, the dissipation must occur on tiny scales, but then why do we see this area of this region of the corona different from this one over here? We know there's a magnetic structure there. There's no plasma, not much plasma on it. So what organizes these into these scales here? And that's a puzzle that is again something I brought up at the end of the book as a suggestion for people to study. This is going to be a worth-selling book in solar physics because all the people that have established their careers in the last 40 years, are not going to want to read it.
isn't this because that you're looking at the blueberry syrup in the cake and not looking at the cherry syrup? That's
Yeah,
also
probably.
in there.
Yeah. Stop mentioning a cake. I'm getting hungry.
Can it also potentially be micro scale physics versus macro? Like
Yeah, but
certain forces like gravity gets heavily involved once you get into the macro. I'm not saying in this particular case, but,
yeah,
couldn't the macro feed back into the micro?
that's a cascade, right?
Mm-hmm.
But my concern about the numerical models that are done is that there's an inverse cascade that's not captured by the numerical schemes, for instance. The question about the connection between the large and the small scales is absolutely one of the biggest puzzles. I mean, I don't know why it's organized. And the other thing I put out in the book is, if you take a multicolor image of the EIT or something in the book, then what you see is coronal holes which are dark. And then you see active regions which are bright red because they're hot. And then you see a whole area of the sun that's not bright red. It's green because it's not so hot. And then you've got the blue, which is the cool corona. Why isn't the sun all gray? How do huge areas of the sun underneath, say, an active region know to be at one temperature and not at another one? That's a real puzzle to me. It's easy to say that heat conduction modulates the temperature because it goes, the energy flux get radiated away, and ultimately there is this T to the 7 halves. So it's natural that you should see some organization, because if I change the energy flux by a factor of 10, the temperature changes only by a factor of 2 or something. So you should see some of that. But even so, I find it quite surprising that the sun is incredibly well organized in the corona. And that's another thing that people say is not, but I think it is thermal. The thermal physics is not really interesting to me because it's the end of the story. It's the beginning of the story for a lot of stories.
Thank you, Phil.
Thank you. Yeah, thanks everybody for coming. I'm really pleased that you all came along. And I will be working for another year at HAO, probably not a lot longer. But if any of you want to come and talk to me anytime, I'm very keen on helping young people with research and just listen to what you're doing. I got nothing to gain. Maybe you have, but I got nothing to lose. I think.
So you said that in line with